Okay, now we're going to talk about hypothesis testing. The main reason for doing this, because the interpretation of the same data can lead to different conclusions. So suppose that you're getting 6 on a consecutive, for example, 5 dice rolls or something. Your friend can claim that, hey, you're doing a trick or something like this, and he can get suspicious. But he can go ahead and say that, no, I'm not doing anything. It's pure luck or something like this. So as you see, you have the same data, but interpretations can be different. So how can we reach the objective scientific conclusions in such cases? There is the need for statistical hypothesis testing, okay, so that we can use scientific methods for decision making. And hypothesis setup and testing is based on one or more population parameters. For example, guessing the sex of newborns, or when you roll a die, whether the probabilities are equal to what you're expecting as general P or not, like 1 over 6 for each of the numbers, each of the phases. That's it. So you first set it up and you go ahead and test it. Namely, it has 4 main components. The first one is the most basic one, is the null hypothesis, what you accept. And then you go ahead and rely on the test statistics, that the data that you gather. And you need to have a rejection region for making the hypothesis testing. This is the confidence that we're talking about. It is called the rejection region here. And of course, you need to have or define your alternative hypothesis, or, okay, is it different than the normal? Is it less than 𝐻0, or is it more than the common probability, or something like this? That would be your alternative hypothesis, which is called H1. So defining all of them makes you have a test, hypothesis test. And if you change one of them, and it means that you will have a new test set, or a new test, a brand new test. That's the idea. The null hypothesis is the hypothesis that being tested, such that what we are normally expecting to happen, if there was nothing interesting, what are we expecting to happen? That's the idea. So be careful. You need to build it before sampling. I mean, don't build it. What is your normal after you get your sample data and you had a look at it. Otherwise, it's like cheating. Don't do it. You need to have your null hypothesis before sampling. So, null hypothesis covers the beliefs before the event had happened. It still holds until it is objected or rejected by the collected new evidence. For example, as long as until one person is deemed guilty, he is innocent, right? That's the idea. Or the probability for guessing the sex of newborns should be around 1.5, right? This is what we're expecting normally. Or the dice rolls, or tossing a coin, or something like this. So those H0 or null hypotheses are defined well before. And the decision about null hypothesis is based on samples taken from the population. So then we're going to decide to reject it or not. So this is called test statistics, which can take different values for each sample taking process. So you can have different values for different sample sets. In other words, that's it. Now, there are, of course, some reservations for errors in hypothesis testing, and we have two types of errors right here. Okay, let's talk about the nice things first. Suppose that your H0 is true and you accept H0. It means that you do not reject H0, which is very nice. Or suppose that your alternative hypothesis is true and you reject H0, which is okay, you did it good. So it means that it needed to be rejected. So far, so good. But there are type 1 and type 2 errors. What are they? Okay, suppose that H0 is true. This is the truth, the truth about the population that we can never know or never be sure. That's it. Suppose that H0 is true, but you rejected. This is called the type 1 error, usually denoted with alpha. And what about the type 2 error? Suppose that H0 should be rejected or should have been rejected because your alternative hypothesis is true. In fact, it is the truth about the population, but you unfortunately accept H0. This makes another type of error, which is called the type 2 error, and it is denoted with usually beta. So the quality of your tests lies in the values of alpha and beta. You want alpha and beta rates to be as low as possible, as minimum as possible. That's what we're aiming. That's what we're dreaming about. But of course, let's see how we do it. Usually, if your alpha increases, your chances of making beta error decrease. So you can see that if you expand your rejection region. So suppose that you have a rejection region like this here. If you expand this, it means that you're like you're making a slack test, okay? Not so strict one, a slack test, and it means that the probability of type 1 error is increasing. It means that you're talking with less confident or something like this. But of course you need to. But at the same time, it means that your beta is decreasing. So if you're increasing the probability of doing type 1 error, it means that you're decreasing the probability of doing type 2 error usually, and vice versa is also holds. What also holds if you reduce the rejection region, that means that you're making like a very strict test, then it means that you're decreasing the probability of having type 1 error, but you're increasing the probability of having a type 2 error in this case because it's becoming so strict. Suppose that you have a new method that works or something like this, but since it is so strict, you will be rejecting it, or you will be in fact, your alternative hypothesis is true, but you're missing the possibility of taking that into consideration because it's like this, because you increase your beta. That's it. The very nice thing about this is if your n grows, significantly, your alpha and beta drops. Both of them will drop. Both of the possibilities will drop, which is very nice. You see, in order to decrease both of them at the same time, the only way to do this is increasing the number of samples you take. But of course, it is costly in a different way, but this is the only way. So usually, type 2, which is called the beta error, lies on the difference from your H0 value, the difference from your H0 value. So suppose that you're guessing the sex of newborns, for example. Usually your zero hypothesis or null hypothesis should be 0.5, and if your difference from this null hypothesis is very significant, difference is very much, suppose that someone is guessing with 99% probability or something, your beta naturally becomes quite low because there is so much difference between so much deviation, so much difference from your H0 hypothesis. So even a few samples are enough to reject your H0. That's the main idea. But suppose that some other person is guessing this with the probability of almost, let's say, 0.5, but a bit more than this. So there is very, very little difference here. So your beta probability, in fact, that person has some kind of insight, but a very slight one. But here, your beta probability is increasing significantly as well. And you need lots and lots of samples in such a reality case, that in such a truth case, that we never know about the alternative hypothesis to prove that our alternative hypothesis holds. In other words, to reject your H0 hypothesis, null hypothesis, you need to have a lot of samples to prove that. If your difference or deviation from your zero hypothesis is very slight. That's the idea, that's the main idea or main issues about the alpha and beta and type 1 and type 2 errors that we can encounter in our hypothesis testing. Okay. Now, you should keep in mind that this is very important. Alpha and beta tolerance levels must be set before you start your testing process. Otherwise, that would mean you're cheating to a degree, okay? Because when you see the numbers, you can, just set your thresholds as anything you like, to reject or to accept H0, reject or not reject H0. That's it. So you need to set them before you start your hypothesis testing process. That's the idea. Now, we're going to talk about, from this point, we're going to talk about large sample hypothesis testing, which is called the z-test, that you're familiar with. And we're also going to talk about small sample hypothesis testing, which is called t-test, and let's focus on their examples as well.